In the previous video of this problem, we solved parts A and B. How much time does the car take to come to a stop? And how far does the car travel before coming to a stop? But in parts C and D, I guess I should point out what we found out was that the time it takes to come to a stop is 3.3 seconds, which I've listed here. How far the car travels, that is to say the delta x to stop. The delta x to stop was 8.3 meters. But we're asked in part C and D about the car after 8 seconds. So it comes to a stop after 3.3 seconds. That's where we stopped caring about the system in the first part of the problem. But if the acceleration is indeed constant, that is to say, if it is continually applied even after the car comes to a stop, well, what's the car going to do? Well, after it comes to a stop, the acceleration is in the direction to the left, and the car will then start to move to the left. This is very similar to what a ball does when you throw it up in the air. It's moving up, but the acceleration is down because, well, gravity's always down. So the ball comes to a stop at the very apex of its motion, and then the acceleration due to gravity accelerates it, so it speeds up as it comes back down. So the same thing is happening here, although it's not as easy to see because this is a car that's moving in the x direction. We're used to thinking of balls going up and down, and that makes sense. But there's fundamentally nothing different about this system than that. It's a constant acceleration in one direction. So the car will move to the right, it will come to a stop, then we'll turn around and accelerate to the left. This is all the work for the previous part of the problem, but let's just draw a picture of that really fast. So if the car starts here, and the acceleration is applied like this, right? What the car will do is it will move, and it will come to a stop. It'll turn around and keep moving like this, right? And it will go past the original point, unless the acceleration changes. If the acceleration doesn't change, it's going to just keep accelerating in the negative direction forever. Alright, so that's the motion of the car. We've thought through it physically. Now, let's see if we can put some math to it. The first thing I'm asked, what is the first thing I'm asked? Assuming that the car starts from the position x is equal to 0 meters, what is its position at t is equal to 8 seconds, right? So I need a kinematic equation that relates position to things I know. And at this point, I know a lot about the system, right? So let me just write down the equation I'm going to use. Delta x is equal to v initial t plus 1/2 at squared. Okay? So I know that v initial is 5 meters per second. I know that t in this case is 8 seconds, right? This is a new time because I'm looking at the motion of the car at a different spot than I did in the first time, in the first two sections of this. The acceleration is still minus 1.5 meters per second squared. So I think I know everything to solve this. The only thing, notice, and this is a little subtle, in part B I was asked for a distance. In part C now I'm asked for a position. Those are obviously related, but they're not the same thing. So let me unpack this delta x just from the definition of the delta. X final minus x initial is equal to v initial t plus 1/2 at squared. Right? Now, what is my x initial? Well, the problem stated, assuming that the car starts from the position x is equal to 0, x initial then is just 0, and I can exclude that term from the rest of my calculation. So I'm left with this x final, which is what I want. I don't even have to rearrange the equation, it's already solved for me. So this is actually your answer. Not a big deal. If you want a numerical solution, let's put in the numbers. X final then is equal to, that's 5 meters per second times time, which is, this case is 8 seconds, plus 1/2, plus 1/2. My acceleration is minus 1.5 meters per second squared, and then this is 8 seconds squared. Alright, my time squared. So notice what happens here. I've got time to the first power here and time squared over here. So the time, as the time goes on, right, I'm at 8 seconds. As it goes on, the squared term is going to get bigger and bigger and bigger faster than this over here. This is t, this is t squared. T squared is going to grow a lot faster than t. Well, the t squared is associated with this term, which notice is negative, right? So for small t's, this part of the equation is going to be bigger than this part of the equation, and my position will be positive. But as t gets bigger and bigger and bigger, that roll flops because of the square. Apologies. And this part of the equation gets bigger by magnitude than this part of the equation. And we expect the position to go negative, which is exactly what we said physically would happen, right? So let's run the numbers and see what happens. As it turns out, if I do that, I find out that the final position is minus 8 meters, right? So that is 8 meters to the left of my starting position. Let me look at my original picture. If my starting position here is here, the car moves this way 8.3 meters, sorry, this way 8.3 meters, and it comes back, comes back, comes back, comes back, and after 8 seconds, it's over here, 8 meters to the left of its original position. Okay, now I'm asked what is its speed at t is equal to 8 seconds, right? So at the position I'm looking at here, how fast is the car going? Well, again, kinematic equations come to my rescue. I've got this one, v final is equal to v initial plus at. V final is what I'm looking for. I'm actually looking for a speed. This is a velocity, but we can always turn a velocity into a speed. That's not a big deal. I'll show you how when we get there. So again, this equation is already solved for me. So as far as I'm concerned, this is the answer. If you want a numerical solution, you plug in the numbers 5 meters per second plus minus 1.5 meters per second squared times 8 seconds. And the same thing happens here. This term is constant, right? This part of the equation is constant. This varies as t, but notice there's a negative sign here, which means as t gets bigger and bigger, this right part, this term gets bigger or gets more and more negative. So at small t, this one's going to be big, and we expect the velocity to be positive. But as t gets bigger, this takes over, and the velocity becomes negative. So if I run the numbers here, I get that after 8 seconds, this thing is going minus 7 meters per second, right? Which means its speed then is 7 meters per second, which is your final numerical answer. So I solved for the velocity because that's what the kinematic equations give me. I can always get the speed out of that just by taking the absolute value. Alright, so now I believe we've completely solved this problem. The first two deal with motion in the very first part, and then we have motion in the second part for C and D. Alright, I hope this was helpful.